Thank you for your post. My interest was piqued when you quoted University Corporation for Atmospheric Research. Carbon existing in a variety of forms is the very basis of life, and its greatest reservoir. In the atmosphere, carbon fully oxidized as carbon dioxide, fully reduced as methane, and in particulate form as black carbon soot, produces the greenhouse effect, making Earth habitable. This sentence is jam-packed with information. I might have mentioned that when I was first getting into ecology, the thing that scared me the most was the oxidation-reduction reaction, which occurs in nutrient cycling and around which I could not wrap my mind. You mentioned that carbon dioxide is an oxidized molecule, while methane is a reduced one. Let's think about the chemistry of this. Firstly, here are the molecules. Carbon dioxide has one carbon atom and two oxygen atoms. Notice that the oxygens each have 6 blue dots, 6 electrons in valence, and the carbon has 4 available. So what we're seeing here is that each oxygen is double bonded to the carbon atom because we have 2 full sets of electrons between these atoms. Okay, and the color relates to the donation of electrons from each atom type. Now let's look at methane. So here we see the electrons color-coded again. Here we have a nonpolar molecule where we have electron sharing such that this molecule no longer engages in chemical reactions because the hydrogens are happy with their 2 electrons in valence and the carbon is happy with its electrons, 8 electrons in valence. Okay, that is the definition of a nonpolar molecule. So remember that the periodic table will help you to know that hydrogen is on the top left. Group 1, period 1, has 1 electron to donate. Hydrogen can accept 1 electron to become noble, the state in which the outer valence of electrons is filled, and therefore the atom becomes unreactive until an atom or molecule with greater electronegativity comes along. Literally, comes close by. Remember, this is based on physics. Atoms that are not close together cannot react and overcomes the electron bonding. Carbon is the magical element that has 4 electrons to donate and 4 to accept in its outer valence. Therefore, the bonding arrangements are almost limitless. Organic molecules are so named simply because they have carbon in them. Organic in this context has nothing to do with the contemporary organic foods movement. Finally, oxygen, period 16, has 6 electrons in valence. It can accept 2 electrons. Note that elements on the right side of the periodic table tend to accept electrons from elements on the left. Furthermore, since oxygen has more electrons than carbon, to begin with, it is said to be more electronegative. I think this image is a great summary for what you are talking about. So when we're thinking about the periodic table, hold on one sec. And thinking about oxidation-reduction reactions, really we are using oxygen and hydrogen as examples because of how they behave. But other atoms, other elements can behave in the same way and cause reduction or oxidation. So firstly, when we think about these terms, remember that electrons are negative subatomic particles. So when you gain an electron as a molecule or atom, the overall charge is reduced because it becomes more negative. When electrons are lost, this is called oxidation, but the charge is the loss of electrons increases the charge. So when we talk about oxidation here, the best way I can think about it is that because oxygen is on the right side of the periodic table, it tends to steal electrons in chemical reactions from atoms on the left side. Therefore, we call it oxidation because when oxygen is around, what typically happens is that electrons are lost from the other atoms. Oops, sorry about that. And so we can look at hydrogen in the same way. Even though we think of hydrogen standing alone as a single atom is +1. It has 1 electron in valence. Hydrogen, when it's around, offers that electron into chemical reactions, and therefore it reduces whatever atom or molecule it's interacting with. Okay, so if you add 2 hydrogens, you're adding 2 electrons, reducing the equation or the chemical reaction. If you take those hydrogens away, then you're oxidizing. So, getting back to the quotation, carbon exists in a variety of forms, is the very basis of life in its greatest reservoir. In the atmosphere, carbon fully oxidized as carbon dioxide, fully reduced as methane, and in particulate form as black carbon soot produces greenhouse effects, making Earth habitable. Our focus here is not on the specific chemistry of the atmosphere, but we are in an integrated science course, and this is a great example of how all science disciplines are interconnected. Rather than focus on the pure chemistry of oxidation-reduction reactions, our punchline here is about the bonds and the outcomes they have for the atmospheric temperature. When we say that the atmosphere traps heat, we are really talking about the ability of the molecules in the atmosphere to hold heat in their bonds. Both carbon dioxide and methane hold heat. Which one do you think holds more heat? Which one has more bonds? Methane. We can go into another whole conversation about sources of carbon dioxide and methane, both of which are greenhouse gases, but for now let's accept from our chemistry learning that bonds represent potential energy. The more bonds in the atmospheric molecules, the more energy. When bonds are broken, these bonds release heat, thereby warming the planet. Finally, one quick thing about the soot, the carbon particulate matter. This actually prevents solar radiation from transmitting to the Earth. Furthermore, there is a speck of dust in the center of every forming cloud. The water molecules adhesion to the particulate matter and to each other, cohesion. Scientists debate whether a negative feedback of climate change will be an increased cloud cover that will cool the planet. That is for another conversation.